Okay, so this is going to be our Chapter 15 exam recitation lecture, just covering topics that are relevant to our kinetics chapter leading into our first exam. And I'm going to keep it fairly straightforward. So let's see here. Question number one. Some of the questions will be fairly fast explained, and some are going to have a little bit more process to them. If I can now advance. Okay, so first question. What's the overall order of the following reaction given the rate law below? And this rate law is we have NO gas plus O3 gas goes to NO2 gas plus O2 gas, and the rate is going to be equal to the rate constant K times the concentration of NO to the first power times the concentration of O3 also to the first power. So when they're asking for overall order of the following reaction, and we have the rate law, this is fairly straightforward because we know that both of the order of the reaction for the NO is 1, and the order of the reaction for the O3 is also 1. And the overall order for a reaction is the sum of all of the components. So with respect to NO is 1, with respect to O3 it's 1, but overall it's 1 plus 1. So in this particular case, this is going to be second order. Pretty easy start. Let's make it a little bit more complex. Write a balanced reaction for which the following rate relationships are true. So in this particular case, we have a couple of different things going on. And the place that I like to start is kind of rationally. And what does the negative mean versus the positive? So first off, on our first term, we have negative 1/2 of the change in the rate of concentration of N2O5 over time. What's the negative mean? And where does that mean that that particular component of the reaction goes? Does it go towards the reactants or does it go towards the products? So what we're really evaluating here is a rate. Remember that. So the deltas mean change in concentration over a period of time or over time. So if we have a negative change in concentration over time, see if I can make this this pen work again. Here we go. Okay, now we've got it going. Because we have a, well, this isn't working at all now. Okay, well that's super not working. Have to bear with me here. Okay, now that I've figured out some technology, hopefully that doesn't happen again. Once again, going back, we have a negative term and then we have our two positive terms. And this positive term is by default +1, so we don't specify, but there could be a +1 there to accompany the +1/4 and -1/2. -1/2 means we have a negative change in our concentration over time, which means it's decreasing in concentration over time, meaning it's being consumed. So in this particular case, if we have a negative term, the negative term, because the change in concentration indicates consumption of this particular compound, that would make it a reactant. So we're going to put N2O5 on the reactant side. And if it's positive, which we have for the following two terms, that means that the change in concentration is indicating an increase in the amount of these compounds over the course of the reaction, which would indicate that it's a product, or they are products. So we have now know what goes where. N2O5 is our reactant, and the NO2 and the O2 are products. So now that we know that, what else can we take away from this? Well, let's look at these coefficients, the 1/2, -4th, and 1. What do these mean? Well, these are, remember, derived from the molar coefficients in the ratio of our reactants and products. So the 2 is pulled down from the molar ratio in our equation. The 4 is pulled down, and the 1 would also be pulled down. So if we want to set this up, where we have our N2O5 on our reactant side, and then we have our NO2 and our O2, if we were to now make this an equation, we would pull the 2 out, we would pull the 4 out, and we could pull a 1 out, but we just leave it blank because 1 is assumed if it's left blank. And that should be our final answer for this particular question. Problem. Next problem. All right, half-life question. So carbon-14 has a half-life of 5,720 years, and this is a first-order reaction. So if a piece of wood is converted 88.5% of carbon-14, how old is it? So this is clearly going to be a half-life question. We've got a half-life of a T1/2 of 5,720. We know that's first order, which is important because our half-life equations depend on the order of reaction. We know what percent of carbon-14 has been converted, and that gives us everything we need to know. So let's start off. What we need here when we have this kind of question right out the gate is we need a rate constant. We need K to really proceed. So what's the equation for K for a first order reaction? K equals 0.693 over our half-life. And let's just go ahead and plug this in and determine K really fast. So 0.693, our half-life is 5,720 years. So our K is going to be 0.000121 years to the -1, or 1 over years. So that's a pretty slow rate, but that's a pretty long half-life, 5,720 years. So now that we have the K for this reaction, we can move forward with the rest of the problem. And the rest of the problem is about percent consumed and the amount of time it takes to get there. And the equation which easily best fits that is natural log of the concentration of whatever we're interested in at time point t over the concentration of that molecule initially, which is what our naught is, equals minus K times time, in whatever unit we're working with, in this case years. So at time t would be the point at which the concentration of t is in question in this equation. So now that we have this, another really important point to note is that whenever you have the ratio of concentration at time t over the concentration at time naught, we can express this, if we don't have the actual concentrations, as a percent. And that's what's happening in this question. So if a piece of wood is converted 88.5% of carbon-14, how old is it, is the question. And this is where a lot of people go wrong, because they'll plug in 0.885 into the term that I just put in parentheses. And that would be incorrect, because that is an indication of A naught over AT. So because they asked converted 88.5% of carbon-14, if we arbitrarily had 100 being our number of units for A naught, and we consumed 88.5% of those, that would leave us 11.5%, or 11.5 units of that 100, meaning the term we need to plug in is 0.115, or 11.5%. So now that we have that little barrier hidden out of the way, what I like to do is rearrange the equation to solve for the variable I'm interested in before I substitute. I find it to be a lot cleaner. So what I'm going to do is I'm going to isolate time t by dividing both sides by -k and moving the t over to the front. So natural log of this concentration of A at time t, concentration of A initial over -k, and I can just go and say natural log, and for this term that I've got in parentheses, because this is the ratio I made over here, plug in 0.115, or 11.5%, and then divide by -k, which is 0.000121, and this will give you 17,852 years. Oh, and remember, units on the rate constant would be 1 over years, which is why our units for our final time is in years. And units for our concentrations cancel each other because they're identical to one another. So it's a nice, neat solution. Okay, so that wasn't too bad. Let's see here. Let's move on. Let's do something a little different. Ooh, this is a fun one. Determine the rate law and the value of K for the following reaction using the data provided. So let's see here. Ooh, this is interesting. So to make it easier to read, this got moved. So you can see what these are actually should be aligned. So our first column is our initial concentrations of S2O8 2- in moles per liter. Their second column is our initial rate. That's what the i's are all indicative, the small lowercase i's. Excuse me, initial concentration of iodide in moles per liter. And the third column is our initial rate of reaction at those initial concentrations in moles per liter per second. Okay, so now that we got that clarified, we can start this party up. So let's see here. What are they asking for? Determine the rate law and the value of K. Okay, so to do this, we have to experimentally, and this is a nicely done experiment, evaluate each of these individually to determine their individual rate laws. If there's 0 order, first order, second order. And to do that, we have to hold the concentration of the second one set so that the only one is changed at a time. So let's start with looking at, let's see here, this one. Let's hold our iodine set. So iodide is going to be held at the same concentration, and at those two concentrations, we've changed the concentration of S2O8. And we have two initial rates of reaction for the set of reaction conditions. So we're not even going to have to look at this anymore. We're going to get to focus only on the concentration effects of S2O8 because there are no concentration effects associated with the iodide in this particular scenario. So knowing this, let's make a simple ratio 0.44 as our initial concentration on this side and 0.30. And this is going to come out to 1.467. If we do the exact same thing with the equivalent concentrations, 0.44 associates with 6.65, being our moles per liter per second. See, 6.65 over 4.54. This ratio is 1.465. So functionally, these are a 1-to-1 ratio. As you change concentration, it has a direct 1-to-1 effect on the rate of reaction. So because this is 1-to-1 ratio, this is going to be first order. So with respect to S2O8, it's going to be first order. That's a terrible one. Let me try that again. Let's do this again and hold. Let's see if I can draw with a different color here, just for funsies. Okay, so let's do the same thing here. We're going to hold S2O8 fixed in terms of concentration, initial concentration, and that's going to give us the ability to manipulate the rate of reaction exclusively with the iodide, and we can evaluate their ratios compared to our rates at those reaction conditions. So we've got 0.42 over 0.21 equals 2. Right? It's a doubling in this case. And our rates are 6.65 over 3.33, which is functionally 2. So this is also a 1-to-1 ratio and is also going to be first order with respect to iodide. So now we know the order of reaction for both of our reactants that we're interested in here. So let's see here. Now that we have this, I'm going to do a little erasing. Make a little bit of room. Okay. So remember, rate equals K of our reactants. And in this particular case, S2O8 to the first power, which I'm just going to leave. Oh, shoot, I'll draw it in. You don't need to draw this in. You can leave it, but I'm going to write it in just for clarity's sake. Oh, 2 minus. Also. So to finish this question, all we need to do is find K. And we have all of the data we need. We actually have more data than we need. So we can just substitute in an initial concentration for S2O8 and an initial concentration for I, and we know what the rate is for both of those. For 3 different conditions, we can do it for this series of conditions, this series of conditions, or the series of conditions, and all 3 are going to give us the same answer. So just for convenience sake, I'm going to go with the first one, because why not? So I'm going to solve for K and just say that the rate initial is going to be the concentration of, or initial concentration of S2O8. Sorry, acclimating to a tablet, over the concentration of iodide. Now, once again, these are all just first order with respect to each of these individual reactions. If these were second order, we'd have to include exponents here and here, but we don't need to because they're 1 in this particular case. So I'm just going to plug this in. Let's see, rate for the first is 4.54, and that's moles per liter per second, over 0.30 moles per liter times 0.42 moles per liter. And we can just solve this. And remember that units-wise, this is going to be moles per second over moles per liter squared. So that'll cancel, and you'll get 1 over seconds over moles, which can then become moles to the negative 1 over times second to the negative 1. So this is also the correct units for K for a first order reaction. And this will be 36. So now that we have this, I can rewrite the entire thing to be rate equals 36 moles per liter per second inverse, seconds inverse, times the concentration of S2O8 raised to the first power times concentration of iodide, also raised to the first power. And that'll be the answer for this particular question. That was fun, so let's do it again. All right. Let's see here. Determine the rate law and value of K for the following reaction using the data provided. And this time we're going to use NO, oxygen gas, and NO2. So nitrogen monoxide, oxygen, and nitrogen dioxide. Let's see. I'm going to switch back to red because somehow that seems appropriate. Okay. So let's hold start with this being set so that we're looking at NO initially. So we're going to evaluate from these two initial concentrations of nitrogen monoxide and also using these two rates. So I'll start with 0.060 over 0.03 and the corresponding, which is a ratio of 2. And then if we do the exact same thing, 3.42 times 10 to the minus 2. And just make sure you're in the same place here. So because I started with 0.06 to make a nice positive integer in my ratio out of convenience. You can do it the other way if you want to, but I just find it's easier to make positive integers whenever you can in these cases. 8.55 times 10 to the minus 3. And you will see that that is 4. So a doubling of the initial concentration of nitric oxide quadruples the initial rate. So this is a second order reaction with respect to nitrogen monoxide. Now if we hold nitrogen monoxide concentration, initial concentration set, and evaluate the initial concentrations of oxygen and the initial rates if we manipulate oxygen, let's start with 0.011 over 0.05. Oh, there's another O in there. Whoop. 0.0055. And that's going to be a doubling of our initial concentration of oxygen. And if we look at, let's see, 0.011 to 1.71 times 10 to the minus 2 over 8.55 times 10 to the minus 3. This is also a doubling. So we have a 2-to-2 ratio, which is a 1-to-1 ratio, which means this is a reactionist first order with respect to oxygen. So I'm just going to make some notes here. Now we're ready to just get this party started. Once I can get rid of all of this drawing. I might not get rid of every last bit. Oh shoot, I'm so close, might as well now. Okay, so now we have this, remember, rate equals K times the concentration of NO squared, because it's second order with respect to nitrogen monoxide. We got our oxygen gas, which is the first order, and now we're ready to party. So all we need to do to find K is rearrange to solve for K, and we can substitute any of our sequence of reaction conditions. I'm just going to stick with the first one because it's first and is easy for me to visually reference. So K equals rate over concentration of nitrogen monoxide squared over the concentration, initial concentration, of oxygen squared. Oh, not squared, first order. And so the rate of reaction in this case would be 8.55 times 10 to the minus third moles per liter per second over 0.030. Get the unit in there. Moles per liter squared. So that's going to be squaring our unit there as well. And 0.0055 moles per liter squared for our oxygen. That is incorrect. We're not squaring that. Okay, fixed it. So let's see here. Let's just go ahead and do a solution because we'll have calculators. 1,727. And if we cancel everything out here, moles per second over moles cubed, the moles per liter there will go away, which will make that squared, which is the same as 1 over seconds over moles per liter squared, which is the same as 1 over seconds times 1 over moles per liter squared, which we can then just rewrite in the standard form, moles per liter to the minus 2 and seconds to the minus 1. Okay, so this should be the answer for this scenario. So it's always nice to know where to start with a problem. So if you're looking at a rate problem, you're going to need to find the rate constant if you don't have it. So just think of it in those terms. Good place to start. Okay. Next problem. The first order decomposition of dinitrogen monoxide at 1000 Kelvin has a rate constant of 0.76 per second. If the initial concentration of dinitrogen monoxide is 10.9 moles per liter, quite concentrated, what is the concentration of dinitrogen monoxide after 9.6 seconds? All right. Well, there are a couple equations you could use here, but I think the easiest one for us, recognizing that this is a first order decomposition reaction, and right out the gate, we're looking at a change in concentration over time. I think the relationship natural log of the concentration of A at time t equals negative kT, t being time, not temperature, that would be capital T. And it's only a reaction condition and specifies this particular rate. It's not needed for our calculation, plus natural log of concentration of A at our initial time point, or A naught. So, knowing this, what do we need to do? What are we looking for? Well, maybe say what we have. We know it's first order, which is how we have the specific equation. We have a rate constant K. We have an initial concentration of 10.9 moles per liter. And we have a time of 9.6 seconds of reaction. So what we're trying to find is that concentration at time t, which is the term that we already have set up for very conveniently in this place. So we're going to keep our negative out in front because negative is just -1. K, 0.76 per second. Time, 9.6 seconds. Seconds will cancel, removing that term, or those units from the term, plus natural log of the concentration of is going to be 10.9 moles per liter. And we can solve this in steps. It's going to be -7.296 plus 2.389, that's an ugly 9, which is -4.907. And at this point, this is where a lot of people forget that we haven't actually finished the problem. Because naturally, you shouldn't think, aha, I have a negative concentration. That would be silly, because we can't go below 0 for concentrations. And you might have forgotten that we have a natural log over here. So the easiest way to get rid of the natural log at this point is to raise both sides to exponent of e. This is going to eliminate this term, just like multiplication and division. And what we will get for the concentration of, in this case, dinitrogen monoxide at 9.6 seconds is going to be 7.4 times 10 to the -3 moles per liter, which is much, much, much lower than 10.9 moles per liter. That also makes sense intuitively, since the half-life, the rate constant is 0.76, which is fairly fast, and we let the reaction proceed for almost 10 seconds. Next question. The rate constant for the first order decomposition of N2O is 3.40 per second. What is the half-life of this decomposition? Now you might think, Dr. McGill, in the last question, the rate constant was 0.76. You'd be right, but that was at 1,000 Kelvin. We don't know what the temperature is for this reaction conditions, but it's a different reaction condition. And because you can change the rate of reaction with temperature so easily, or pressure or other conditions, but in this class we usually look at temperature, it's okay to change these constants. Don't be curveballed by that necessarily. So in this particular question and set of reaction conditions, the rate constant for this first order decomposition is 3.40 per second. What is the half-life? Well, this is where you just have to remember the equation for a half-life for first order reaction. And thankfully, half-life for first order reaction is 0.693 over K. And this is probably where you're thinking there has to be something that makes this harder, but there isn't. It really is that easy because we're set up to solve for what we want. We only have 3.4 as our K. That's all we need because we have our 0.693 over 3.40 per second equals 0.204 seconds. So about 1/5 of a second is the half-life of this particular reaction under the set of reaction conditions. Sometimes these questions really are this simple. And finally, last problem. this one's a little bit more involved. The first order rearrangement of methyl isonitrile is measured to have a rate constant of 3.61 times 10 to the minus 15th per second at 298 Kelvin, and a rate constant of 8.66 times 10 to the minus 7th per second at 425 Kelvin. Determine the activation energy, or energy of activation, for this reaction. So right out the gate, we know we need to find activation energy. And we have two sets of reaction conditions. We have one at 298 Kelvin and one at 425 Kelvin, and we have rate constants for both those. So right out the gate, your brain should start thinking, we have a T1, we have a T2, we have a K1, we have a K2, and that should prompt the following relationship: natural log of K2 over K1 equals activation energy over R times 1 over T1 minus 1 over T2. And R is our ideal gas constant of 8.314 joules per mole Kelvin. So now that we have this, what I'm going to do is just do a quick rearrangement to solve for activation energy to make it super easy. So activation energy, I'm just going to multiply both sides by R and divide both sides by the entire term involving temperature. So what we should end up with is natural log of the rate K2 over K1 term times R over 1 over T1 minus 1 over T2. And now we're set to jet. This is just going to be a little bit of arithmetic now. So the hardest part of this is keeping what is 1 and 1 and 2 straight in your head, right? So you can make that semi-arbitrarily, but I like to do it in a way that gives me a slightly higher rate to begin with. So what I'm going to pick as our one condition is, let me just double check my rationale here. Let's see. Let's just arbitrarily call this one 1. So this will be 1, and this will be number 2. And that'll hold for both K and for our temperatures. So K2 over K1, K2 comes first. Here we have T1 minus T2. So that's where people mess up. They tend to do things in the same sequence, and they end up with something wrong because of that. So let's go ahead and start it out. Natural log, what's K2? K2 would be 8.66 times 10 to the minus 7 per second over 3.61 times 10 to the minus 15 per second. And then that's going to be 8.314 joules per, going to be a little tight, mole Kelvin. And then over here we have 1 over T1. T1 is 298 Kelvin minus 1 over 425 Kelvin for our T2. And then it's just crunching numbers. And if you crunch through this and you get all your math, let me just throw kelvins in here. Per second over per second cancels out, so we don't have to worry about our units when we're doing our natural log transform. So we're just going to end up with joules per mole Kelvin over 1 over Kelvin. So kelvins will cancel, and we should have joules per mole as our activation energy, which is the unit we want. And this will come out to 156,951 joules per mole, or if you're doing sig figs, about 157 kilojoules per mole. And that's going to be the solution to this problem. And that's really all the problems that I think, types of problems that I want to review. The exam will have some other questions, obviously, as well, but I think they're more situational and a little less intensive calculation-wise. If any of this threw you for a curve, please spend some more time working these styles of problems on the homework platform. Make sure you get your repetitions in with the solutions, getting everything set up, solving, and also make sure you have your equations memorized, because you are responsible for knowing the equations for these reactions. And that's it. So I'll be seeing you all. Well, I guess I won't be seeing, because it's an online class, so I won't physically be seeing all of you. But study hard, and best of luck on the upcoming exam.